Okay, so we've talked already a lot about invariance and variability, and I've kind of alluded to this multiple times, but now I'll kind of walk through the exemplar model approach to speech perception and what evidence there is, or what evidence originally inspired the idea that the model can work for natural human speech perception. So this is going to sort of flip every assumption that people used to have about speech perception and categorization on its head, and say that, well, we're not worried about finding what's invariant in a speech signal to try to figure out what people are saying, but instead we're going to look at the variability that we get and preserve that variability that we get in speech, and presumably in other forms of categorization as well, rather than boiling that variability away down to something like properties or prototypes to define a category. So in this model, speech categories are defined by extension, which is to say, like a B is simply every single token of B that you've ever heard before in your life and categorized as a B. So rather than consisting of properties or prototypes, speech categories are defined by their exemplars, and that's where the name of the model comes from. Each individual member of a category is known as an exemplar of that category. And I'm saying this again here, but your mental representation of a B consists of every token of B you've ever heard in your life, rather than the specific acoustic or articulatory properties of those tokens. So it's easy to, say, well, a B is a B because, when you produce it, you bring your lips together, make a closure, and stop the flow of air through your mouth as you produce it. And then you're also getting voicing in some sense down at your vocal folds. But even when you stop to think about that, it starts to get a little bit tricky. Remember, we learned in 341 that a lot of B's are not voiced, especially at the beginning of a word in English. But in the middle of a word, those B's are voiced. So is this really a definitional property, even though it seems like it? Acoustically or articulatorily, you might get B's where you didn't totally make closure when you produced that B, but in context you figured out that it was a B, like it might become something more like a bilabial fricative or what have you, which is sort of more common maybe in other languages, but it could happen in English or whatever language you happen to speak. You still think of that as a B, even though it didn't show you those properties that we normally think of as canonically defining what a B is. I've got an analogy here about the way the Phonetics field project for this class used to work, which is as more of a field method sort of project where you go out and you talk to a speaker of a language that you don't know, and you record or write down everything they've said over time until you start to figure out like what counts as meaningful in the language in terms of the sounds that they're using to contrast with one another. So in that approach, if you do go out and do field work in whatever language, it's useful to sort of transcribe all of the variability you hear right from the start before making assumptions about what or might not be contrastive in the language. You don't want to kind of get stuck in the assumptions that you use for your own language in terms of contrastiveness, right? Because it could work entirely differently in your consultant's language. And over time, you kind of start to figure out, well, there's kind of some consistency over here in the B's, and we can kind of rely on them to be over here in like acoustic space, and then the D's are over here, so on and so forth. So maybe there's a contrast there. But maybe there's something like, a palatalization contrast, which you're not used to hearing at all. And it'll take you a while to kind of figure out how that works and how it relates to sort of like vowels and consonants in context with each other. And preserving that variability at the start enables you to sort of preserve that contrast without sort of tossing it away in favor of some other assumption you might have about how a category of speech sounds is defined. Okay, so I'm going to give you one model of how this is supposed to work, exemplar style, and sort of the terms it uses to describe the process that happens when we categorize things. But like I said, in exemplar models, categorization happens on the fly, so it can evolve over time. It happens always in time, and it evolves over time as a category might change, basically its contents. So rather than looking at specific properties that a speech token might have to define it, we'll talk about stored memories of speech experiences as traces. So this is a memory-based model. Each memory you have of an experience of speech in your life leaves a trace in your mind, like your footsteps on the hiking path up in the mountains or what have you. each trace is going to be linked to a category label, like a B or an E or an A or something like that. And I guess I'll point out here that this is one part of this model which can be, at least theoretically, quite useful, and that you don't need to link a speech token to a linguistic category per se, but you could sort of link it up to like a socially defined category of some sort, like, well, that's a man versus a woman, that person's Canadian versus American, that's an older speaker, that's a younger speaker, so on and so forth. So you can link it, the same trace in memory, to multiple different kinds of categories, whether they're like socially defined or whether they're linguistically defined. For now, I'll try to keep it relatively simple and just talk about this in linguistic terms, but just keep in mind those possibilities are there. These incoming speech tokens, the things that we have to figure out how to categorize, are known as probes. A probe will activate the traces in memory that it is similar to, and this activation is going to be proportional to the similarity between the trace and the probe. So I'm going to show you an example on the next slide of what this might look like graphically using the Peterson and Barney data. But basically the important part here is similarity between trace and probe. That's how we're going to do the categorization process. So that's going to provide sort of the foundation for the categorization process. And that's also kind of the tricky part of this model, is to figure out exactly how similarity is judged if you're not sort of clearly defining properties as definitive for a category or not. You still have to use something to kind of get that measure of similarity. So traces that closely match a probe will be activated a lot. Traces that have no similarity to a probe won't be activated much, if at all. And again, this is kind of easy to see in a formant space diagram like this. So these are the vowels from the Peterson and Barney data set. And let's just pretend that there's some speaker out there. Let's pretend that Peterson and Barney are like aliens from another planet, but they still categorize things like human beings. And these are all the vowels they have heard in their lives, because they got these from their recordings in their speech production project back in 1952. For some reason, aliens came to Earth and they visited Michigan. Who knows why? Anyways, just to get people to say vowels. This is a probe. This is a new thing that Peterson and Barney have never heard of before, and it falls in this particular spot in the formant space. And we'll just have kind of a simple model of similarity here, which is just like distance in the two-dimensional formant plot. So what you do in theory is you say, well, I'll take the probe and then I'll figure out how similar it is to every single trace in memory. This is not really an efficient model, but it's like intellectually pure, which is somehow satisfying. And also it's satisfying because we can kind of make predictions based on math in terms of how it works, at least in the case of vowels. But let's say we're going to compare how similar this probe is to each trace in memory. So every single one of these vowels will make a computation of similarity, and basically the ones that it's similar to or close to in this space will be highly activated. They'll get sort of high rating, they'll get very excited, and then the ones that are far away will not get excited at all. They're like, that's not anything like us, so why do we care? We're just going to sit where we are, and we'll leave it to you guys here in the part of this diagram to sort of get activated and compete for classifying this new vowel as one of your own. So basically... so there's like this other part of this particular model, which is kind of interesting to think about, that the combined average of activations from exemplars in memory will be summed to create an echo of the perceptual system. And then this echo kind of winds up being sort of like the abstract consciousness you have of your experience. You're not exactly hearing exactly what came into your mind, but rather that in combination with the response of your mind, sort of this back and forth measure of similarity between the two. So that echo will give you more general features than either the traces or the probe by themselves. It's kind of an meeting halfway sort of approach. You're half hearing what's outside there in the world, and you're half hearing what's already stored in your mind that's similar to what just came into your ears. So there's a metaphor you can use for this. This is from the work of a guy who's an interesting figure in intellectual history named Francis Galton, who is a British guy, I believe, who was primarily working in the late 1800s. And so he did a number of different things. So if I'm not mistaken, he talked about the wisdom of the crowds, which is also kind of an applicable analogy to this. So that particular example Francis Galton was looking at was like at a county fair or something like that. And if you don't know what a county fair is, it's like a small scale, small town version of the Calgary Stampede. And back in those days, they had a contest where you'd say you'd look at a pig, and people would come around at the big festival and guess the weight of the pig. And I guess, like, whoever gets closest to guessing the weight of the pig wins a prize of some sort. I don't know if they won the pig itself or not, but so the idea was that, or the observation that Francis Galton had, is that if you look at any individual's guess of the weight of the pig, they might be way off, they might be close, but there's a lot of variation in there. But if you average over all their responses, it turns out that people are actually pretty close to the exact weight of the pig when you just calculate their average. So there's some sort of like overarching wisdom that people have that's not instantiated in any one person, but the whole crowd by itself can guess pretty well. And this other analogy kind of follows the same logic. So he did this stuff which would no longer be considered politically correct in this day and age, but it's similar to what is happening when you have an echo in your perceptual system when you hear some speech token. So he, this is in the early days of photography. What he would do is he'd take pictures of people and kind of overlay the exposures on top of one another to try to get an average image of particular kinds of people. And yeah, he was doing this to classify like different ethnicities or races, which is now largely considered offensive for hopefully obvious reasons, but this is not a racial case. So he's trying to define what a particular kind of person looks like with sort of averaging these three dudes together. The average he gets looks like this, and you can kind of see features of each one of these guys in the average, but this whatever abstraction dude doesn't look exactly like any single one of these other individual actual people. So what kind of person is this? Maybe you can guess simply from the fact that these pictures are similar to begin with, like in terms of their framing and whatnot. But these guys are all criminals. So the idea was that this is sort of like, this is what a criminal looks like, this guy. And people like that are sort of, criminal looking, I guess. This is similar to what's supposed to happen with speech in your head, in that when you hear like somebody saying E, your mind responds with sort of like an average sense of what an E sounds like, but one that has not been actually produced by any specific person in memory. This is how your mind generalizes on the fly. Okay, so getting back to where we were before, we're activating traces based on how similar they are to the probe, and some of these traces are linked to these different, every trace is linked to a different category label in memory. So these are the id traces, these are the ed traces, these are the ad traces. So based on whatever one they're linked to in memory, they activate that category label. And then you sum up all the activations of the traces for a particular category label. And so if the egg category has the most activation, then that one wins. If it has slightly more than I, slightly more than A, slightly more than all the other categories, then you hear the new probe as an E token. And that's how you identify it for future categorization. So that new egg gets added into the mix of the egg category, and it'll shift around the whole average of that category a little bit, right? It'll move it slightly towards itself. The kind of main point here, though, is that this is a very democratic model of categorization. There's no privileged members in terms of prototypes or what have you, and it's not abstract. You're not thinking in terms of properties. Instead, you're using every single token in memory to help you categorize the new tokens. They all get involved to some extent and kind of have a vote in how the final decision ends up. As I mentioned before, any single trace can be linked to different kinds of category labels. So you can use the same underlying memory system to, say, determine whether that's an E versus an A, or an E versus an I. And then, you might have to say, I have to judge, or it might help for you to know like whether a speaker is Canadian or American, because their E's and their Is might be in slightly different places to begin with. So you can listen to how somebody talks to make that decision too. If you apply this sort of approach to the Peterson and Barney Vowell data, if you remember, this is just a homebrewed thing that I did at home one day. and using the original data from that data set. But the prototype model got about 50% of those vowels correct. When you get more variation in there, when you're actually doing this with all of the exemplars in memory, then the exemplar model can classify 81% of those vowels correctly. Human beings are doing 94% correct with a similar sort of task. So they're still doing better, but the exemplar model is kind of pushing us closer to human performance. So this is democratic as well with respect to the fact that all properties of all exemplars are supposed to play a role in categorization. So it's not only democratic with respect to which exemplars get involved in a category, but also which properties get involved in a category. You don't have to make assumptions that, like, say, well, F2 matters, but F0 doesn't. So there are not definitive properties of the speech tokens. They all get involved because it's the whole token that's kind of responding to the probe that's coming into the system. So the prediction here is that the sort of non-invariant properties of speech categories should have an effect on speech perception. We normally think about how to define speech segments in terms of the properties that are supposed to canonically define it. So we think about a B as closure of your lips with voicing to prevent air from flowing out through your mouth. But, your actual experiences of a bee involve a lot more than that. So they involve who's speaking. They involve like the context, the speech sounds in which that bee was produced. You can even think about it in terms of like the room in which the bee was spoken. So psychologists have done tests like this, which are kind of interesting to think about. And it's going to be weird in this particular semester of this class, but if you have studied a topic in a particular class, and normally in my classes, individual students will pick the same seat to sit in every single time for whatever reason, you will do better on a test in that class if you are in that same room and if you are in that same seat than if you have to take it in another classroom at a different time or what have you. Somehow that feeds into your knowledge of the subject, the way you've learned it. That kind of becomes part of the encoding of that knowledge in your mind. So I tried to show you how this works in terms of speech with this continuous word recognition experiment. So you might remember that we were listening to a sequence of words, or hopefully you did this at home before this lecture as I instructed you. But you were supposed to say, well, is each word a new or an old word in the list?
Pride.
Yeah, and then the part of this that I didn't fill you in on before you did the experiment.
Pride.
Oops.
Core. Whim.
Is that
mate,
these were all produced
hair, rut
by different speakers.
Bear.
Yeah, so the ones
bear
that are repeated in the same voice are generally speaking easier for you to recognize as repeated words in the list rather than words that switch voices between repetitions. So this is funny because like nobody would come up with a theory, well, in the old days, nobody would come up with a theory of linguistics that says, beings are defined by not only their sort of physiological properties, like what you're doing with your articulators, but they're also defined by like who actually says them. But our minds take that information into account. So we actually store the information of who said a particular speech sound as we encode it in our memory, and that makes those particular tokens easier to recognize on future repetitions than, say, the same sound produced by, or same word produced by a different person. So this recaps what I just said. Some words were presented in new voice, others were presented in the old same voice. This was originally found by a group of researchers named Palmieri et al. Back in the early 90s. Repetitions are identified more quickly and more accurately when they're presented in an old voice, or the original voice that the word was presented in the experiment. So the implication here is that you are storing voice and word information together in memory, and then you will do better at recognizing that token when you get both of these elements together, rather than just independently or in a more abstract form, I guess you could say, when you hear it from a different speaker. So these are the data that I have gotten before this year from this class in terms of what percentage correct you get on this task. So in terms of the new words, people get close to 100% at identifying what's new as opposed to old. For the repeated or old words, it's about 93% correct for the same voice repetitions. and it's more like 73 or 74% correct for different voice repetitions. So it's a fairly considerable drop off. And I've done this with lots and lots of subjects over the years. We're probably around 100, 150 at this point. So this is pretty reliable, statistically speaking. This is looking at sort of the same difference between the lags and how long it takes you to hear the repetitions. So this is repetitions within 10 stimuli in the list, because I've used the same list consistently over the years. So that's about 93% to like 77%. So that's like a 16% drop off in accuracy when it's repeated in a different voice. The same voice tokens are pretty persistent in memory. We get almost the exact same level of accuracy after a 10 stimulus repetition for same voice repetitions, but the different voice repetitions start to drop off a little bit more. This is like 76 or 77. I don't know what I said, but this is more like 71% correct. So those different voice repetitions get harder to recognize more quickly over longer periods of time in the list. Okay, so I can give you some other interesting interactions between voices and word tokens in memory. So there's a study that came out in 1994 by Lynn Nygaard and some of her colleagues who trained listeners to identify talkers by their voices. So listeners came into a lab and they spent multiple days just learning to identify different talkers from the sound of their voices alone. And then, like on the last day of the experiment, they tested the listener's ability to recognize words spoken in noise by the talkers they learned to recognize and the talkers they didn't know. So this is like that word recognition and noise task we did a while back with the Sumby and Pollock demo, looking at audiovisual speech perception. So you hear a word, it's noisy, it's not easy to pick up what's being said, but the words were spoken by two groups of people. One was the talkers they had learned to recognize, and one was the talkers that they didn't already know, so just other random people. And as you might expect, people could identify the words spoken by the familiar talkers more easily than the words that were spoken by the unfamiliar talkers. And you can kind of think about this, like there are people you know in your life obviously better than others. So if you may be used to listening to your parents' voices quite a bit, or the people in your family, and when you hear them in noisy listening conditions as opposed to some random stranger on the street, it's simply easier for you to understand what, say, like your dad is saying, as opposed to just Mr. Whoever. So the idea is that in real life, people kind of store this voice information together with the words that they were hearing, and they're using those voice properties to perform this word recognition task. The flip side of this is also true, that when you are listening to speakers speaking in a foreign language that you don't know, you are not able to sort of differentiate or identify those talkers as well as listening to just random people who are speaking a language that you do know. So language affects voice recognition, and the ability to identify voices affects word recognition. It works both ways. One interesting finding in this line of research is that variability is not problematic, but it's actually useful. So when you get more variability, when you're learning to do a perceptual task, it actually winds up being helpful. It helps you generalize better over the long term. So it's best not to let the relationship between words and voices get too close in learning. And a classic example of this is studies that have looked at how to train Japanese listeners to discriminate between R and L in English. And I've kind of mentioned this issue before, but in Japanese there is neither an R nor an L. There's an alveolar flap, which is kind of similar, or the most similar sound to both of those, but Japanese listeners kind of don't have anything to rely on in their native language to split these two apart. So if you are a Japanese learner of English, it can be a bit of a struggle to get this contrast. As if any of us have learned a foreign language, there's other issues or other contrasts in foreign languages that we don't know that can be hard to wrap our minds around. This one has been studied quite a bit, though. It's kind of a famous difficult contrast for the Japanese speakers. In the 80s, people were kind of on a kick saying that like Japanese listeners couldn't really get this contrast no matter how hard you tried. So there are studies like Strange and Dittman from 1984 where they trained Japanese listeners for a long time on this contrast using only one speaker and didn't find any improvement. In the 90s, when this exemplar model started getting rolling, people tried to incorporate more variability in these training paradigms. So Bradlow et al. Used training methodology where they used 5 different voices for the Japanese listeners to listen to. They also used multiple phonological contexts, so they're putting R's and L's in onset position, coda position, and different consonantal clusters. And they also gave them a lot of training, 4 weeks of training with money if they did better than some sort of baseline performance. And they did find that people actually got better. The Japanese listeners started to pick up this contrast between R and L over time. So it's possible, and it's likely that the greater variability in the training materials help them generalize to sort of new tokens, as would be predicted by the exemplar model of speech perception. So lots of variability in training will lead to better classification of novel tokens, but it might slow down your learning process at the beginning, but over time it kind of pays off because it forces you to learn how to incorporate greater variability in categories. Variability in training has also been shown to help the perception of synthetic speech, which is not all that easy, and I'll talk more about that in our final lecture for the course. It has also been shown to help people in dialect identification. So this is a study done by a former colleague of mine who now works at Ohio State, but she looked at how people who have lived in different areas of the United States are able to identify speakers of different dialects. And of course, as you might expect, if you've lived in a broader variety of places in a country, it's easier to kind of identify where people come from in that country. This original Bradlow et al. Study also had this interesting finding that perception training passively improved production skills. And this is kind of fun. So this is plotting how each listener in this study did in terms of how they improved their perception versus how much their production improved. So they did like a production pretest at the beginning of the study, and they just said R's and L's in various contexts, and then people like judged how well they had done, like native listeners of the language. And for most of the subjects, there's not a whole lot of improvement. For production improvement, you want the arrows moving up on this scale. There's a lot of perception improvement. So like speaker or listener number 11 goes from like 67% to like 92% correct, which is great. But this person, even though they weren't getting any production training explicitly, gets a bit of a boost in production accuracy. So from like 56% to 60%, so on and so forth. So this person goes from like 74 to like 80. So you kind of get that for free. They were just doing this perception task over and over again, and they got better at production. And this person's kind of funny. Always jumps out, but like they did not that great in terms of improving perception, but their production went way up. So maybe they were just like focusing on the wrong thing in the study. I don't know. But either way, overall, you get this implicit benefit. So to a certain extent, you kind of think of this exemplar model of perception is like this sort of alternative to the motor theory, because the exemplar model of perception, at least it's an alternative to like modularity, such that the exemplar model of speech perception is borrowed from sort of general categorization theories from cognitive psychology, and it can just sort of be applied to like the acoustic features of speech to give you a useful categorization model for speech perception. So it's not really assuming that speech is special in any way, or that you are perceiving speech based on the gestures that people use to produce it. It's sort of just classifying sounds. You don't have to draw that strict of a distinction between the two models, though. It looks like even you could say have an exemplar model applying to like the gestures that people actually use in speech. You just have to work out, well, what are people perceiving about those gestures that make one similar to another? You need to have some sort of metric of similarity. And this model I'm sort of introducing, or this study I'm introducing as like a nice example of how exemplar principles can work in speech perception, and that you get more variability and that leads to better generalization. But it also applies to like a generalization between perception and production. This is sort of a nicer little finding for motor theory than anything else, and that we may be perceiving things in terms of how they're produced as well. So I'll give you another example, one last study from the late 90s. This is from Stephen Goldeninger, who did what was called a shadowing task. So in this task, there was a production side of it where listeners read or produced words in two contexts. So one is that there are subjects in the study who just saw like a list of words and they read out the words just from a script. And then the other condition, they heard a word over headphones and they were just supposed to repeat what they said, whatever it was. So I'm going to label the word that they heard as an X here, and their productions in this context are labeled as A. Their productions in this context are labeled as B. So when they looked at sort of the acoustic properties of these various productions, there's three of them, A, B, and X. They found that the formant values and durations of, say, vowels and segments in the B productions were more similar to the X productions than the ones that were produced in the A condition. So in the A condition, you kind of expect like a, just general abstract sort of canonical version of the word. In the B condition, though, you don't get those canonical abstract versions of the word so much because these B productions are kind of drawn magnetically almost towards these X repetitions or X productions that they heard as the source of their repetitions in this experiment. They also did a perception side, or he also did a perception half of this experiment in which listeners performed an AXB task in which they were supposed to judge. They heard like, dog, 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 where the first token in the sequence was, say, the word dog read by the subjects in the A condition. The X is sort of this original for the B condition, and then the B is the repetition for the second reading condition or production condition. And those listeners are simply supposed to judge whether that X token sounded more like A or B. So this isn't relying on specific acoustic properties. It's just a perceptual sense of which ones sound more similar to each other. And as you might guess, the B productions were judged to be more similar to X than the X were to the A. So when you hear somebody saying something, you start to sound more like they do. You don't just have to repeat it. There's sort of this like magnetic effect. It's called entrainment, I believe, where people start to sound more like each other when they get into conversation with one another. I can also think about this from my own experience because I have moved to different dialect areas of the English-speaking world, and maybe you have too. Over time, when you get into a new context and start hearing people who speak in a different way, your accent will start to shift, often closer to theirs. So the interpretation, there's some other interesting complications for the results of this Goldeninger study, which are kind of fun to think about. Their repetition effects, where the B tokens became more similar to the X tokens, those were more prominent for low frequency words and also after shorter delays. So this is where that echo comes into play, where sort of you're merging the faces together into one average face, or maybe their sounds together into one average sound. The effects of the incoming probe, the incoming example of speech that you hear, they have more of an effect on how you repeat things if they're a low frequency word. So we kind of saw examples of low frequency words the other day where I played you like beer, which is a relatively high frequency word, and I played you tithe. So you probably don't have as many exemplars of tithe in memory as you do for beer. So if you hear somebody say tithe, you're likely to say it more like the way they said it than when you hear the word beer, because you have lots of tokens of beer in your mind, which you can kind of rely on to help you produce another version of beer. So that shadowing imitation in the Goldeninger study is a reflection of kind of the echo, like how much information are you getting from your memory. If you have more information of memory, the more of an effect that memory is going to have on your production. Also, that probe-based activation decays quickly. It's kind of like what we saw for the continuous word recognition results. You lose that token's influence over time relatively quickly, and that activation will also have more of an influence over smaller exemplar sets like low frequency words. So the moral of the story, to wrap this all up, remember, categorical perception was initially used to justify the claim that listeners converted a continuous signal into something discrete, or what we classically think of as categorical. So this
We know the new mayor.
particular utterance would be converted to something like this, which gives us nice, clean category labels throughout, and everything's 100% nice and clear, right? But in reality, listeners don't discard all of this fuzzy, fine-grained information in speech, whatever it might mean to them. Especially, it's been shown for sounds like vowels, so on and so forth. Those perceptual categories that we actually use to function in the human world and the natural world have to be more richly detailed than the classical categories found in phonology textbooks, which, is why it's nice to study phonetics. The phonology stuff still has to be there. We still sort of make these contrasts between sounds, but when the rubber hits the road, we need those details. We need all that to be able to deal with the variability that we actually encounter in real life speech, which comes from a lot of different people from a lot of different places, and includes a lot of people we haven't heard before. In order to be able to generalize to those new sorts of variabilities, we have to have a lot of variability stored in memory and know how to process it. I'm going to stop there with exemplar modeling. We're going to have one more fun lecture to wrap up the semester on speech synthesis, so I'm looking forward to seeing you then. Okay, have a good night.